kind of maybe spend 30 seconds or so and think about this problem. I know we have thought about this, but some solutions, but can you think of some optics-based solutions to the problem that we just talked about? And feel free to discuss, but let's take 30 seconds. And online, feel free to put your ideas in the chat or just unmute yourself and you can say something. So the problem we're trying to solve is the fact that a single solar cell, a single band gap, does not match the huge spectral range of sunlight. In other words, if maybe I'll leave it. Here. Let's see if you have some ideas. Oops, sorry. Did that. Any thoughts for those of you here? Anyone online? Don't see any, but
making the bottom layer thicker have any difference?
If you make the bottom layer thicker, it might absorb more light, but it won't solve the fundamental problem. It's not going to absorb the higher energy photons, unfortunately, just because you still suffer from the thermalization problem. This problem, you'll still suffer from this problem. Because the band gap is too small. It doesn't match all the energies. So what I mean, let me maybe rephrase the problem. That wasn't super clear. If you look at the solar spectrum, you have a huge range of energies. Think about photons coming at vast, order of magnitude, right? At 300 to maybe several thousand nanometers. That's the wavelength, but that's also directly inversely proportional to energy. So when you have such a huge diversity of energies, you cannot absorb all of them with a single band gap. This is a fundamental problem. Let's see, someone said something on chat. Nathan said, use a prism or grating, separate the light spectrally and make 3 devices connected in parallel. Yes, I think that's a good idea, spatially, sorry. Yeah. That's a good idea. And that's along the lines of what I'm saying. So let's kind of clarify what he's saying. What he's saying is that if I have some light coming in, if I have a device here that can then, I'm going to draw an angle, separate out the colors. So I send the green here. Blue here. And then if I can use different solar cells to absorb them. Of course, I'm drawing this as in a schematic, but you get the idea. So if you can separate out the colors, which represent the different energies, and absorb them differently, then you can avoid this problem. And then they can be completely dependent. So you can connect them in series, parallel, also a combination of the above. Now, sometimes, by the way, you might need to connect things in some series parallel combination, because if you completely separate them, then you have essentially 3 different panels, and handling current from 3 different panels is complicated from the power electronics perspective. It gets really expensive. So there are other considerations that come into play. That's a good suggestion. And that's the direction I'm gonna go to. The solution I'm going to talk about is something a little bit different. It's using something called a diffractive spectrum splitter, also called a polychromat. It's a term that we came up with. So you can see the sunlight coming from the top. It's a diffractive structure, and it separates the colors, but also concentrates the light. So you can see this is all colors. And here you get red and you get the blue. And I'm just showing red and blue as schematics. It can be, it represents different wavelengths of light, different energies of photons. And here you use different solar cells to absorb it. So this is solar cell 1, this is solar cell 2. Now, for those of you in class, I actually brought one that you can look at later. But I'll show you what it does, and I'll show you some pictures. So this is an example of what it looks like. And for those of you online, this is kind of what it looks like. And what it does is, and you guys can come and look at it later, is I'm treating the projector as sunlight. So you can kind of see there what it's doing. It's separating out the visible part of the spectrum, which is visible to your human eye, which is reds and greens and blues. And the dark part of the spectrum is infrared, which is invisible to that. So I can put a solar cell in the dark part, which has like germanium, and the higher band depth cell, which absorbs the visible, slightly violet, I can get higher efficiency out of the system. That's an example of one of these devices. And this is what I'll talk about. And you can all look at it later. So this is an example of one of those devices. It looks fairly complicated, but what it does, and you can see it's kind of microstructure with many different levels and so on. In this example, there's a 1.4 micron height with about 10 micron width. It's a one-dimensional structure, so that's why you're seeing a line scan here. And what it does is that light is divided into two buckets. So you can see one bucket, this is position. So one bucket is on the left-hand side, another bucket is on the right-hand side. Okay, and on the left-hand side, you get the visible band of light, and on the right-hand side, you see the infrared band of light. The light is simply separated out. In this case, the concentration factor is only 2x. Right? You're collecting light from this entire position and allocating it to half the size. So it's a concentration factor 2x, but in addition to concentration, you're separating the energies of photons so you can absorb them more efficiently. And that's exactly what I just showed you on the screen. And you can look at the optical efficiency, which is of course very important. How efficiently can you actually do the separation? So this is just showing, okay, at different wavelengths, I can allocate it to the left or the right, depending on the color of the light. So for instance, if I have 400 nanometers, I have over 78% efficiency that goes to the left-hand side. Whereas if I have 900 nanometers, I have a probability of something like 78% that's on the right-hand side. And average everything, I get an overall optical efficiency of something like 74%, which is not terrible, but of course, we'd like it to be 100%. That's hard to do. Those are experimental. Those are simulation results. Now, for the actual experiments, we have to fabricate them, and I won't go into much detail, except that these are just microscope images of the example I showed you. So these are lines. So in this, the reason to make them one-dimensional like this is, as I showed before, here what happens is that half of light gets concentrated on one half, the other wavelength gets concentrated on the other half. Right? That's what's happening. Now, if I think about the motion of the sun, I want to ensure that I want to only track in one direction. So I want the daily motion of the sun is to be in this axis, which is my degenerate axis, so I don't need to track the sun that way. So that's why it's one dimensional. In this axis, I only have to track seasonally because the sun moves across the sky. Okay? That's why it's one dimensional. It doesn't have to be. If you have a two-axis tracker, you can make it two-dimensional as well. And here there are some more images. Here you can see a more detailed image here which looks like piano keys, but they're somewhat complicated, but similar to the schematic that I showed you before. And they are made using grayscale lithography, which Amartya is very familiar with. For instance, the way you make it is you use a UV laser source, you impart energy to the photoresist on a glass wafer. It's a lithographic process. The more energy you put in, so that's a higher energy. This is slightly lower, is the lowest. After you do development, you get different depths. So you get the deepest, and you have most energy going into the resist. When you have slightly less energy, you get a slightly less deep, and lowest energy, you get the shallowest. And by controlling this extremely precisely, you can make very complex structures as shown here that you can imagine. Okay, so you do a laser-based lithography, you do a development, you end up with structures like this. And then, of course, for mass manufacturing, there are other steps that need to be done, but I won't talk much about it. Oh yeah, actually I have one slide. So for mass manufacturing, one would actually make this in a roll-to-roll fashion, very similar to what packaging films and so on are made. Newspapers used to be printed. Essentially, you have a roll-based system, which goes this way, and then the pattern is on a drum which rotates as shown here. And it presses into a polymer that's heated up. And the polymer then conforms to this pattern and creates the pattern that I showed you before. But now you can make it in huge volumes at low cost and so on. So lots of nice properties of this kind of an approach. And people make these things for decorative films and things like that, holograms and things like this. Now, how do we actually characterize this? We characterize them in a setup which kind of looks like this, a photograph setup. First of all, like I said before, instead of taking it out into the real world, we have to have some standardized measurements. So that's done with an artificial sun, which in our case is simply a xenon lamp. Now, the xenon lamp, the light comes out and it's conditioned, which means that you want to kind of clean it up and make it look more like the sun, like direct sunlight. And that's what all these paths are for. You're allowed to expand over a pretty long distance. And then you have your device set up here, and then you have solar cells there. Okay, so that's kind of the setup. And before we actually put the solar cells in, we actually have to measure the optical performance to make sure it's actually working the way it's supposed to. And this is what it looks like. Those of you are in class, you saw it in person. But basically, you have the device here. It's illuminated by white light, just as I showed you before. And you can see the image is formed here, and a more detailed image is shown on the right here. But you can see the dark parts are the IR bands. These are the infrared parts. And the light parts are the visible bands. So now I can put two different solar cells with two different band gaps and absorb them accordingly in order to get higher efficiency. I'm only showing two for the purpose of simplicity. Of course, you can think of doing more as well. So, of course, as I said before, the first thing is we want to make sure that this is actually working as intended. So in order to do that, you have to not only take an image, as I showed you, but look at the energy of the photon as a function of position. This is done using spectroscopy. So we have a spectrometer, and you can see in this, photograph, there's a fiber input to a spectrometer that is on a scanning stage. And this is scanned across orthogonal to the lines of the polychromat or the spectrum splitting element. And at each location, we collect a spectrum. And then we can compare it to the simulation that I showed you before. And there's a track to set this distance, which is kind of like the concentrator. This is like concentrator to the solar cell location distance, which I'll come to shortly. Now, let me go back. And oops. And the measurements look like this. So on the left-hand side, I'm showing you the simulated data, which is the same thing you saw before, where you can see the two buckets. High energy photons are on the left, the low energy photons on the right. They're physically, spatially separated. Now, when we do the measurements, at every position here, we have a spectrometer. So every line here is a spectrum that's collected on the image plane. And then you move over and collect another spectrum and so on and so forth. And put them all together, you end up an image. And you can see, okay, all the high energy photons on the left-hand side are the lower energy photons on the right-hand side. And they match relatively well. Of course, there's some small differences, but otherwise they're pretty good. That's our first confirmation that, okay, what we're thinking about in terms of theory actually works. Then from that data, one can extract efficiencies simply by summing up the power in the left-hand side divided by the total power. And this is the measured and the simulated plots you saw before, and you can see the comparison. They're pretty close. They're within about 5% or so. And that makes sense. The left-hand side has all the shorter wavelengths, higher energies. The right-hand side has all the longer wavelengths, lower energies, as expected. Right? Now, Now, of course, we are interested in putting solar cells in and seeing what happens. Oops. So here we use two different cells with two different band gaps. One was a gallium arsenide cell with a lower band gap, and a gallium indium phosphide cell. So this is showing the external quantum efficiency as a function of wavelengths. So the gallium arsenide, of course, can absorb out to about 900 nanometers. So it can absorb the lower energy photons in addition to the high energy photons. But in this example, we are not using it for the high energy photons. So I'm going to separate them out, right? The gallium indium phosphide, of course, cuts off at a shorter wavelength around red, 650 or something like that. So you want to only absorb the shorter than the red, the visible band. Now, what happens? So on one side, I have gallium arsenide. The other side, I have gallium indium phosphide. And what happens is this. First experiment was a reference measurement. So here you're seeing the electrical measurements, IV curves of a reference solar cell. Left-hand side is gallium indium phosphide, right-hand side is gallium arsenide, with no spectrum splitting, no concentration, nothing, just a beam. Okay, so basically you have the solar cell, one solar cell here, another solar cell here, light simply just got hitting it. Just measure the current voltage. So that's the voltage, you apply voltage bias, you measure the current density. You measure the current divided by the area of the solar cell. Okay. Simple. So you see normal things that we expect to see. You have an open circuit voltage, which is here, and you have a short circuit current here. And you can, a couple of things I will point out here are that the open circuit voltage of the gallium indium phosphide, oops, for some reason my thing is open circuit voltage, the gallium phosphide is higher than the open circuit voltage of gallium arsenide. That makes sense because my band gap of the gallium indium phosphide is higher. Remember, the open circuit voltage depends on the band gap. On the other hand, my short circuit current is actually lower. It's the opposite. And that may also make sense because my gallium arsenide can absorb more photons over a larger range than the gallium indium phosphide. And you can actually see that in this curve here, right? My gallium arsenide has a bigger envelope. So that determines the short circuit current density. Whereas the band gap here determines the open circuit voltage. So the shorter the wavelength, higher the open circuit voltage, higher the band gap, right? Inversely proportional. Okay, now, of course, what happens is that you take the polychromatic, it's a slightly different polychromatic. I'm going to skip through this. What happens when you put the spectrum splitting element in? This is what happens. You see the reference curves, same as before. You put it in, you get higher open circuit current. Now, why are we getting higher open circuit current? Because we're concentrating the light. Keep in mind, so I'm going to draw the system again. This is our concentrator, and that's one cell, there's the second cell. So I'm taking light from an area that's twice as big as the solar cell. I'm assigning to the source. So because I'm concentrating the light from twice as much area, I'm going to increase my current by at least about a factor of 2, not exactly because I lost this and so on. That's not perfectly efficient. So in fact, quite a significant loss. You can see that it's not double as much, right? And same thing happens here. It's a smaller increase for the gallium arsenide because you're already absorbing quite a bit. Now, on the open circuit voltage, there's very little difference because the concentration factor is so small. It's only 2x. It doesn't really, I don't know if you remember, but we talked about the open circuit voltage being proportional to the logarithm of the concentration approximately. So because 2x is pretty small, the change in open circuit voltage is relatively small. Now, what we are actually mostly interested in is this, is the power, right? Now, power is simply voltage times current, power generated. And of course, there is a peak point with bias, which is the maximum operating power. And you can see that has gone up quite tremendously, which is good. That's what we're looking for. Same thing for gallium indium phosphide as well as for gallium arsenide. The improvement in gallium arsenide is smaller than gallium indium phosphide. And the reason is because gallium arsenide already has a pretty big spectral coverage. It can absorb many more photons. So for gallium indium phosphide, the improvement is more significant. But you put it all together, the total expected power increase is about 20%, which is quite significant in the scheme of things. Even a few percent is important, so 20% is quite rather large. So again, now you can appreciate some of the details of what would involve in kind of proving things out. Now, this is all simulation. In actual experiments, it's a little bit different. There's a picture of the polychromat. It's a different device, so I'm showing the results from this device. And these are the measured images, the efficiency there. You can see they're separated, similar to what you saw before. I'm going to skip it. And you can see pictures of the solar cells here. So the device is there, light is focused. There's a distance of about 10 to 12 millimeters. I forget the exact number right now. And you can see the gallium arsenide cell here, gallium indium phosphide cell here. They look a little bit different. These are all produced at the National Renewable Energy Laboratories. And these are the measurements. Clearly, these are actual, not the simulation, but the measurement. You can clearly see an increase here, similar to what was predicted. You see a slightly better increase here, better than predicted. Okay, so far so good. And of course, most importantly, when you put it all together in the power, you see an increase in the power as well. And the measured total summed increase in power is about 16%. Remember, the prediction was 20%, 60%, so it's pretty close. That's still pretty impressive. So we're pretty excited about this. Now, I mean, there's a lot of detail here, which I'm not terribly important. So I'm going to skip all that. And I want to talk about a couple more things. So the next question is, okay, what sort of efficiency is possible? Now, by the way, this was predicted by some folks, actually Henry, C.H. Henry in 1980s. He was actually working at Lucent or AT&T, I can't remember. But either before, I think before AT&T acquired Lucent, that's what I remember. But at that time, they had some fundamental research. So it's an interesting plot. Now, what does this show? What it's showing is on the horizontal axis is energy from the sun, the energy of the photon. So it's plotting the spectral from the sun in a slightly different axis. On the horizontal axis is the number of photons per unit area, per unit time, per unit of wavelength. So of course, larger the energy, the fewer the photons. Okay, this is the cumulative. So larger the energy, the fewer the photons I have because they're shorter in the wavelength. Now, but what he is saying is that if I have one band gap, my best, and this is assuming a concentration factor of 1000x, I can get a maximum efficiency of 37%. But if I have two band gaps, I can get up to 50%. If I have three band gaps, I can get up to 56%. If I have 36 band gaps, which is pretty crazy, it's kind of starting to be science fiction, and you can get 72%. Those are incredible numbers. You know, we're pretty far from it, but those are the goals. But inspired by that paper, we actually did some simulations to show that, okay, if you had 4 bands, which is shown on the right-hand side, this can actually be done practically. You can get, I forget, something like, you know, close to 30, close to the theoretical limits. But not exactly, because making these, there's a lot of fabrication challenges and so on. And I want to, before I talk about that, I want to show a couple more things, and then I want to talk briefly about the, oops. So there are a few papers that I will link to in the class. They're not quite there. One is using this 3-band spectral concentration. I just want to show very quickly. the results. So here the example was that we designed a device where the light is concentrated into 3 bands, not 2. This was experimentally done. In this case, we used a gallium indium phosphide, gallium arsenide, and silicon. Silicon being the lowest band gap in this example, which is unusual. And how does it look? You can see the devices, and in this case, now you have 3 humps instead of 2 humps. And you have 3 pieces where you're dividing the light. Portion of the light's here, portion of the light's here, portion of the light's here. And the measurements are similar to what I showed you before. We have power density of the 3 cells. That's a reference increased with the polychromat. Reference increased the polychromat, and so on and so forth. So gallium indium phosphide, gallium arsenide, silicon. And yeah, so that's a good example, and there's some interesting details there. And the last thing I also want to show very briefly is that you can also take these things outside and do outdoor measurements. So I just want to very quickly show how we did that, which might be interesting to some of you. So I'll post these links later on. I just want to show one last thing. There we go. So here is how we did the measurements. We had a tripod and a way to track the sun. So here you can see the polychromat and the solar cells. This is how we did the measurements. And we had a way to align them to the sun using the student at that time was an undergraduate student, a visiting student from Germany. She came up with a protocol using these alignment masks that you see on the right-hand side to align and track the sun very carefully. So this is a very interesting experiment, kind of difficult to do, but she was able to do it and show that you can get very nice improvement in efficiency, which is interesting. Now, I'll post a link to this paper, these 2 papers. Finally, I just want to show one alternative approach. This is an approach from a group in Germany, where they are doing something similar to what Nathan suggested in chat, which is using a grading-based splitter. I'll also put a link to this, but I just want to very quickly show their approach. Let me zoom in here. So here, what's happening is that you see all the sunlight comes in, different colors, and they're using the first cell here absorbs the highest energy photons, but instead of allowing the other light to pass through, it reflects it. So the lower energy photons reflect it, and then you have a second cell that's absorbing it here. Part of it's a pass through and absorbed in the next cell. And of course, there's some light that's reflected off. So it's a different way to do it with essentially kind of like not having any significant optics other than something called a dichroic filter, which reflects the alternative, the complementary colors. And they showed some nice results here. Let me see. Yeah, they made these different dichroic filters. So here is a good example where you can see the low frequency light, which is the lower energy. High frequency light is the higher energy, right? Light comes in. Some of the high energy lights reflected off. The low energy light passes through. So that was the main contribution in this paper. And there's some interesting results, which I won't talk much about. Let me see if there's one more thing. Now, this is the same idea. So they also have to analyze a lot of the tracking and so on. But anyway, I'll post these things now, and I'll stop it. So we'll end the lecture a little bit early today. And I just want to make sure that you're all prepared for your final presentation on Thursday, which is the commercialization